When a car's speed triples its kinetic energy at 1/2 mv squared. Hmm. Yeah, 9 times. Increases 9 times. Remind you guys why that's the case. Guys, what is the formula for kinetic energy? Yeah, 1/2 mv squared. Okay. Okay. So now, if you know how to read proportions, you get the answer right away. Because a factor of 3 in that v, that's what speed is, right? The v for velocity. If you throw a factor of 3, that factor of 3 gets squared. Guys, what's 3 squared? 9. That would be the answer. Okay. I'll give you guys a numerical example. What if the mass is 2 kilograms? And let's say the initial speed is about 5 meters per second. Okay. Let's go with calculation. So initial kinetic energy could be 1/2 times 2 kilograms. It's like a little toy car. And 5 meters per second squared, or being squared. Guys, how much kinetic energy is that? How many joules? 25. 25 joules. Right. Now, what if, let's get a new speed here. Let's keep the same math, but I'll say V new is triple that, 15 meters per second. Okay, you do that? So what is the new kinetic energy? Well, 1/2, it's the same 2 kilogram vehicle. Okay, but now it's going 15 meters per second, and that speed's being squared. Okay. Well, 15 squared is like 225. That 225?
Yeah, so
Goes like that. Okay. Now, okay, is everybody okay with that so far? Okay. Now, I wonder what is the ratio of these energies? Well, 225 compared to 25, we just divide it. We're going to get 9. Is that 9? Okay. Right, so if you triple the speed, you get 9 times the energy. There you go. You also say it takes, you have to burn 9 times the gasoline to get up to 3 times the speed. I think. Right, too. All right. Points on the board. Oh, yeah. All simple machines ideally work on the principle that what? Yeah, nice, nice. All right. So these are all true statements that apply to different scenarios, but simple machines is yeah, work input could match work output. Do you guys remember rigging up some pulley systems in this class? That's a type of simple machine. Okay. And you could lift something very heavy with a small input force. The catch is, guys, what was the catch? You had to do what? Pull lots and lots and lots of rope. Yeah, length. Yeah. So you pull lots of string on your side and the weight moves up very slowly. But if you multiply the force you pull, the small force you pull times the large amount of rope you pull, you get that product. And then you multiply the large weight times the small distance it moves up, you get that product. At best, they could be the same. Work input equals work output. That's also called conservation of energy. Yeah. Got Gian, Cole, Spencer, Big Boy Spencer, Kai. How many joules of work done in a box? Got 25 Newton force for 3 meters. Yeah. Let me just multiply it. This doesn't work force times distance. Well, actually, it's a special kind of multiplication. You guys remember dot product? It's a dot product, which means it has to be in the same direction. So you just multiply the parallel components. So you can lift something with some force, some height. If you push something forward, it'd be the forward force times the forward displacement. Yeah, so force times distance, 25 times 3, 75.
Right.
That'd be joules. Ligma Spencer, 67. Big Boy Spencer, Gian Spencer. How much power to do 40 joules of work in 5 seconds?
That's it for life.
Yeah, that is a real Spencer. Well, the Spencer for the nails is the real one.
Yeah, 8 watts. Okay. So you guys remember power is work over time. So power could be a rate of energy transfer, another way to think of it. So 40 joules divided by 5 seconds, yeah, gives you 8 watts. You guys ever seen an 8-watt light bulb? I bet it would be pulling 8 joules per second off the grid or out of the battery. Anna, Ligma Spencer 67, Gian, Spencer, hi. Where does the satellite in elliptical orbit have the greatest kinetic energy? Ooh. Yeah, point closest to the planet being orbited. Okay. I do need to give it is a better picture than the picture you guys have there. Okay. So maybe here's a planet like Earth, and then maybe here's a satellite in pretty highly elliptical orbit going around. Okay. So definitely elliptical. Okay, so here, draw a little satellite here, it's going around, beep beep. Okay. Now, I got a few questions for you guys about this, guys. If you add up the total mechanical energy, let's call this a closed system. The planet satellite system is a closed system. Is the total mechanical energy the same everywhere around? How many of you guys think it is? Who says it's the same mechanical energy all the way around?
Nope.
Yeah, it's the same total mechanical energy. Okay? Because mechanical energy can take different forms. One form is kinetic, another form is potential. Okay? So over here, guys, right over here, it maximizes what type of energy? Potential energy. That's like usually U I use in this class, or sometimes you see PE. Okay? And it has a little bit of what kind of energy? Kinetic. And that would be something to do with its motion, something to do with its speed. Okay? One half mv squared here. Okay? That could be called the apogee when it's furthest away. Now the perigee is when it's closest. So how about over here? Okay. Over here has a lot of what kind of energy? Kinetic, and a little bit of what? Potential. Okay. Okay. So yeah, if it's a close distance, like a small height, a small potential. Right. And a large kinetic means it has a huge speed. So over here has a huge tangential speed. Over here has maybe kind of a small tangential speed. Okay. All right, elliptical orbits. For my AP students, I tell my AP students that I've seen it asked as an AP question multiple times in the past. So look for that. Anna, Big Boy Spencer, Gion, Spencer, hi. Ooh, three flames. What remains constant for a satellite in elliptical orbit? Yeah, the total mechanical energy. If you add up the kinetic plus the potential. Yeah. Now, individually, all these other values vary, but if you add it all up, it's the same total mechanical energy. As long as it's a closed system, that would be true. Yeah. Anna, Big Boy Spencer, Gion, Spencer, Kai. Machine puts out 100 watts of power for every 1,000 watts input. What's the efficiency of that machine? Yeah, 10%. Okay, so 100 divided by 1,000, wouldn't that be 0.1 as a decimal? It's called 10%. 10%. And maybe the other 90% goes to like waste heat, usually is a common. Right. Cole, Big Boy Spencer, Gion, Kai, Spencer. Potential energy is the energy an object has because of its. Hey, ooh, conformity.
No, I put the wrong one.
Yeah, location, height. Right. I remember the localized version went MGH. The more universal forms like negative GMM over R. Okay. But so somebody with like where it's located. Okay. Nothing to do with how fast it's going. That was kinetic energy. Okay. This blue one, somebody picked is thermal type energy. It's another form. Yeah. Control energy. Cole, Anna, Gion, Kai, Spencer. Table tennis ball launcher is fired. Compared to the force on the ball, the force back on the launcher is same force. Is that Newton's third law of motion? Equal and opposite forces. Same force. Has to be the same force. Tabletop tennis ball launcher is fired compared to the impulse on the ball, the impulse on the launcher. Ooh. Wait. Also the same. Here, let me convince you guys that's true. Impulse is also the same. Hey, guys, what was impulse? But what does that mean? That's a change in what?
Velocity.
Momentum. Change in momentum. Yeah. Right. Now, sometimes you see physics textbooks use capital J. AP just reintroduced that too. Right. A lot of times I'll just call it delta P as a change in momentum. Right. Delta P change in momentum. Right. And there's sort of two expressions you guys have seen this. This could be what times what or what times what. What's one of them? Yeah, mass times change in velocity. Yeah, mass times change in velocity. Okay. As long as you have a constant mass, which is usually the case.
Force times time.
Force times time. That's right. A force multiplied by some time interval that that force acts for. Yeah, great. Also, if you ever see a graph, they show all over the place on the exam, force in newtons versus time in seconds. Okay. Yeah, this graph could look like anything. Oftentimes, the force builds up and then dissipates, so like a variable force. Because what property of this graph also tells you the impulse. So, the what?
Errors.
Yeah, area under the curve. Right? If it was a constant force, that would be a rectangle shaped force times time. Okay, you guys remember that? So, wait, what was the? I forgot the question. Right here. Yeah, the ball and the launcher. Okay, so let's go back to this ball and this launcher. So maybe I got the launcher here, and here's the ball, right? And then pow, right? Some equal and opposite force. Right? Oh, hey guys, is the force forward on the ball the same as the force back on the launcher? It's the same magnitude force. Does that act for the same time interval on both objects? Yeah. Well, that's the same. That's the same. This whole thing's the same. It's the same impulse. Right? Right. I got Anna, Gian, Big Boy Spencer, Kai, Spencer, Triple Fire. Momentum of an object.
Low.
Mass times velocity. Oh yeah, that's velocity. Right, P equals mv. Right, mass times velocity. Right, Cole, Big Boy Spencer, Gian, Kai, Spencer. Velocity of a moving object doubles. What else also doubles? The momentum. Right? Right. So, guys, momentum is mass times velocity. So if the mass stays the same and the velocity doubles, then shouldn't the overall momentum double? Right. Well, what about these other ones? Let's look at kinetic energy. Guys, if the speed doubles, does the kinetic energy change? Yeah, but not by a factor of 2. By a factor of what? 4. Yeah, because 2 squared. Because you have to square the speed, right? 1/2 mv squared. Right? So a factor of 2 squared is like, that'd be 4 times the kinetic energy. And then acceleration, isn't acceleration a rate change in velocity? So you can't really address that unless you know some kind of time interval that this happens in. So that one's not super applicable. Yeah, momentum. Yeah, momentum. Big Boy Spencer, Cole, Kai, Gian, Spencer. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small compared to the cannonball. Why? Yeah, let you guys go. Yeah. So the forces are equal and opposite. You guys got that right a few questions ago. Therefore, the impulse is equal and opposite. Right. But the cannon has so much more mass. So really, this is a Newton's second law question. You guys remember acceleration is force acting on mass? Same force, different masses, different accelerations, different final velocities. Cannonball flies out fast. Cannonball, or the cannon itself recoils out slowly. Yeah. Second law. Okay. Hey, does anyone have a question on that? Guys, if you have any questions on any of these, just raise your hand, let me know, and I can write more notes on paper or something like that. Got Big Boy Spencer, Kai, Cole, Gian, Spencer. Actually, what is this? I was thinking it was flames, but what is that?
Nail.
Is that hand pipes?
Just take it.
What?
Painting nails. Painting nails. Like painting nails.
Oh, fingernails. Is that a question mark at the top?
No, it's nail polish.
Oh, all right. It is. Question mark put in my head. It's got some nails. Yeah. Spencer's purple nails. Piece of putty moving with 5 units of momentum strikes and sticks to a heavy bowling ball initially at rest. After the putty sticks to the ball, both are set into motion with the combined momentum of. Yeah, 5 units. Okay. That's just conservation of momentum. You guys remember conservation of momentum? We used to solve a bunch of puzzles. Okay. So momentum was conserved during collisions. 5 units of momentum, it's conserved. Yeah. Okay, got it? 5 units. All right. Now, this is a little bit different. A table tennis ball, except for also 5 units of momentum, strikes and bounces off, bounces backward. That's like this bottom picture. But boing. Right. Now the bowling ball is set into motion with what?
Oh. Oh.
More than five. More than five. Okay. This one's a little tricky. We're gonna draw this one out for sure. Okay, so we got two different scenarios here. Draw a couple bowling balls. Bowling ball here, bowling ball here. Right. Now the first scenario had a little piece of putty coming across with 5 kilogram meter per second of momentum. Like that. Maybe I'll call it P for momentum. Right. Then it collides and sticks. That's inelastic, and the whole system rolls off with 5 units of momentum because momentum's conserved. Right. But the question you guys just got is a little different. Right. What if you have a bouncy ball comes across with momentum is 5 kilogram meter per second, and it boing, bounces off. Bounces off. Okay. Guys, if it bounces off, could it come back with, I don't know, maybe 2 units momentum to the left? Could it do that? Okay. Could it be bouncing back with 2 kilogram meter per second? Like that? Like that? Right. Huh. Right. If that's true, right. Is how much what's the change in momentum of that table tennis ball? 7. Yeah, because it changed direction. And momentum is a what? A scalar or a vector? A vector, which matters too to answer that question. Because it's 2 minus negative 5. Guys, 2 minus negative 5, and then kilogram meter per second. That's like 7. The change is 7. Okay? So that's what was transferred to the bowling ball. The bowling ball actually rolls off with 7 kilogram meter per second. Okay. Or here's another way to look at it. You guys remember how sum of momentum before the collision equals sum of momentum after the collision? Right. Well, before the collision, there was how much momentum in the system again? 5. Right. 5 units. Right. After the collision, here, I'm claiming that the bowling ball is rolling off to the right with 7, and the bounce ball going back with 2, so you call that negative 2. Add that all up. What do you get over here? Also 5. Do you guys see that? Because 7 plus negative 2, 7 minus 2, it's also 5. Yeah. A few ways to look at that. Yeah, so a bouncing collision will typically make something roll off faster. Ooh. That's right. All right, Big Boy Spencer, Kai, Cole, Gian, Spencer. 2 kilogram ball thrown at 3 meter per second. What's the momentum? 2, 3. Yeah, 2 times 3 is 6. Okay, so mass times velocity, 6 kilogram meter per second. Okay, guys good? Hi, Big Boy Spencer, Gian, Cole, Spencer. A collision is elastic. Yeah, all those would be markers of elastic. Okay. Actually, if there's a single answer I do like the best, it's this gold answer. See what says kinetic energy is conserved? That like physics textbook is the marker for that. Right. But these other statements are also true. So you guys know if two objects stick together, that would be definitely inelastic. And if they don't stick together, well, maybe it's elastic and bouncy. Right? Also, no lasting deformation. So here, give you guys a visual over here. Here's an example of something that's very, very close to perfectly elastic. It's just, you guys see how bouncy that is? Like super bouncy? Yeah, so momentum's conserved, and it would be anyway. But kinetic energy is also pretty close to conserved here. Okay? You see how the balls don't change shape? If they change shape, that would be deformation. Okay? And deformation you typically see with inelastic. So here's a counter example. What if I have balls of clay? What if I have this ball of clay and this ball of clay? I'll mark it clay, clay. Okay. Okay. And they're coming together. They're collide. Okay. Guys, so these kind of stick together. Okay. And make a what kind of collision would this be called? Inelastic. Yeah. And you guys think that post collision, maybe the clay now looks something kind of like this? Kind of like this? Okay. Ooh, did that change shape?
Yeah.
It definitely changed shape. Is that called deformation? Deformation. Okay. Is the total momentum still conserved in that collision? Yeah, the momentum's still conserved. Okay. But what about a different property? What about kinetic energy? Did the kinetic energy increase, decrease, or stay the same? Decrease, decrease. Right. Do you think that a lot of that energy was converted into this deformation to change shape? Right? It takes some work to smash this clay and mold it and change shape. Right? And that's kind of hard to quantify. So to solve this, if you didn't want to quantify that, what you do is you do conservation of momentum to figure out some of that final velocities. And then after the fact, you can find the change in kinetic energy. It's how much energy went into deformation. Yeah, that'd be the process for that. Right, okay, so you guys good with that? Right, Cod, boy Spencer, Gian, Cole, Spencer. Force of an apple hitting the ground depends on. Yeah, all the speed before it hits, the time of impact with the ground, whether or not it bounces. Want to convince you guys that's true. So let's get it over here. Okay. Oh, here's an apple hanging on a branch on a tree, and right beneath it, down at ground level, down on the ground, they got a vacuum scale. Hey, doesn't a vacuum scale can that read a force? A force? Okay. And then the apple falls. So here it is falling. Right, falling. Okay. And at some point, it's gonna hit the scale. Bam. Okay. And well, then what? Okay, well, something, but the scale's going to read some number. It depends on a number of things. Okay. Okay. So you guys think that the higher it fell from, the faster it will be crash landing? That has something to do with the force rating? It's okay. There's some other answers too, though. Okay. So let's get a formula for force. It's what's one formula you can think of for force? Force equals what? What's Newton's second law of motion? F equals yeah, F equals ma. You guys remember Newton's second law? Right. No, that's a net force, but you guys get the idea. Okay. Ooh. But guys, what is acceleration? Acceleration is whatever what? Yeah, change of velocity divided by the time interval, delta v over delta t. What's that? Okay, so how does that link back to here? Well, the apple has some mass, so that could be the mass of the apple. That just whatever it is, that's controlled. Okay. Ooh, I bet the speed that it's falling has something to do with this force. Okay, so if it fell from a higher height, it'd be falling faster, so that would be more force, wouldn't it? Right. How about hey, how about whether or not it bounces? Okay, suppose it's crash landing right here at I'm just gonna make something up at like 12 meters per second. I just made that up. Okay, you guys get that? What if it sticks to the scale? What's the change in velocity? 12 down to 0. What's the change? Yeah, the difference would be 12, wouldn't it? Right. But what if instead it bounces boing and it bounces back with like let's say 5 meters per second. Guys, now what's the change in velocity? What's 5 meters per second it bounced back with minus the negative 12 that it was crash landing with? Yeah, delta v equal. Yeah, that's right, 17 meters per second. Hey, isn't that more than the 12 it was falling with? Right. Kind of reminds me of the bounce ball against the bowling ball from a few questions ago, doesn't it? Okay. Would that be more force or less force than if it had stuck instead? If it bounces, it's what? More force. It could be up to twice the force it looks like from here. Okay. And last thing is, oh, if you had a slow-mo camera, could you see maybe the amount of time it's in contact with the scale for, which would be a tiny, tiny fraction of a second? Okay. If it was like 100th of a second versus 300ths of a second, that would be that delta t, and that can make a difference also. Okay. That's all the answers right there. So all the above. You guys go with all the above on that one? Okay. I do like that question a lot.
Yeah.
So. Kai, Big Spencer, Gian, Cole, Spencer. Two gliders, same mass, same speed, move toward each other on an air track and stick together. What's the post-collision velocity? Yeah, 0 meter per second. Convince you guys that's true too. Draw this out. And so we got this glider with some mass and some velocity going to the right. And you got this glider with the same mass and the same speed, but it's going to the left. I could vote that way. And these two are going to collide and stick together. Collide, stick together. Well, the guiding principle here for collisions is momentum is conserved. Initial, final. Okay. Okay. So here, we can throw some numbers on here. Here's what if the mass is like 1 kilogram. Also true for this guy, 1 kg. Okay. And the velocity to the right is how about 8 meters per second? This would therefore be negative 8 meters per second. Okay. Here's what's the total momentum in the system? Huh? Well, momentum is mass times velocity, right? So 1 times 8, 1 times negative 8. What's the total momentum? 0. There's 0 momentum in that system. Now, there was a lot of kinetic energy before the collision, but there was always ever 0 momentum. So that has to be true after the collision. Whoops, not squared, just meters per second. There you go. Kilogram meter per second. So they collide stick together. They just come to a dead stop, don't they? Okay, that's all. Kai, Big Spencer, Gian, Cole, Spencer. Right, which has greater linear speed? Horse near the outside or inside of the merry-go-round? Hey, let's check this out.
When you're riding on a merry-go-round, when do you travel faster? When you're on the outside horse or on the inside horse? Or do both horses travel at the same speed? Well, it turns out there's 2 kinds of speeds there. And we can see that with this little make-believe merry-go-round. If I draw a line, rotate the merry-go-round, we see that all parts of the line are traveling the same RPMs, revolutions per minute, yeah? But how about the linear speed, like in miles per hour? Outside or inside going faster? Well, let's put some people here. 1 here, 1 here, 1 here. These little pennies represent you, huh? I think you can see the outside part is traveling faster. If I whip it up a little more, yes, the outside one flies off. A little more. So it's the inside one that is going slower.
And so one of the key things to notice is that there's 2 kinds of speed. You mentioned angular speed versus linear, or sometimes tangential, you'll hear in this case, speed. Okay. Now, linear speed or tangential speed, we use the character V, right, for like as in velocity or tangential velocity. Okay. Guys, what character were we using for like how fast is something turning? What character? There's a Greek letter. Omega? You guys remember omega? Looks like a little curly W, but it's Greek letter omega, right? And these two can be related. It depends on here. Oh, I'll throw one of his coins right here. Okay. And so as this is turning with some omega, okay, this coin at this instant has some tangential speed I can call V. Right? And it depends how far it is from the center. So I can call this distance here R. You guys remember that? Okay. All right, now let's put it all together. What is the relationship among these three variables I just wrote down, this V, this omega, and this R, how do you write them all in one expression? V is equal to what? Omega times R. Yeah, or R times omega, you could say too. Right? So if you know how fast it's rotating and you multiply by the distance from the center, that'll tell you how fast it's going. Like on a radar gun, if you point a radar gun at this or throw it through a speed gate, okay, that's like a linear value right there. Okay, you guys got it. Right. But there's a catch. Because this formula only works if you measure this omega in what unit? It must be in what unit?
Radiant.
Radians per second. Oh yeah, radians per second. Right. You can't do anything with like degrees or revolution. It's got or RPM for that matter. Right. Revolutions per minute. It's got to be radians per second. Got to be radians. What is one radian? Let's talk about that. Right. So, I know that 2 pi radians. Oh, whoops! I meant to ask you guys. Okay. What is this equivalent to? 2 pi radians. Guys, radians is something how far it's turned.
100.
Yeah, 360 degrees. Okay. Or you could say one revolution, which is the R that shows up in RPM, revolutions per minute, one revolution. Okay. Or if you divide everything by 2 pi, 1 radian is approximately what?
Wow.
57.3 degrees. Right? Which now you can link it back to a protractor, because protractors are marked in degrees. So if you sweep out 57 degrees, right about here, okay, this wedge right here, it's about 1 radian. Okay. All right, so it's a little extra context right there. All right, turntables, turntable physics. All right, you guys good on turntables? We're about to find out how you guys are on turntables. Got Anna, Big Boy Spencer, Cole, Spencer, Gian. Which has greater angular speed? A horse near the outside or inside of a merry-go-round? Angular. It's the same. It's the same. Hey, guys, they're all doing the same turns per time. Okay? All the same turns per time. You got all the same radians per second. Are you guys good with that? Okay. Takes them all at the same time to make one lap around. It was Spencer, Anna, Cole, Spencer, Gian. Oh, fire! You whirl a tin can into the string. The string suddenly breaks. What will the can do? The colors match. Which color is it? What will the can do? There you go. Fly off tangent to its circular path. Yeah, just keep going in a straight line. Hey, is that Newton's first law of motion called law of inertia? It just wants to keep moving in a straight line.
Go to the website to make way for you.
Oh yeah. Oh yeah. Centrifugal forces in quotation marks, because I almost never use that phrase. That's an apparent reality to observers in a reference frame that is rotating. Okay. You have to be inside the rotating frame of reference to experience this. Here, I'll draw this out for you guys. Okay. So let's go back to a merry-go-round. Here's a merry-go-round. Okay. Obviously, we're up in a helicopter looking down on this, right? You guys see this? We're looking down. Okay. Here's the center of the merry-go-round. Okay. And let's throw some handlebars on this. Okay. And maybe here's you hanging on to the handlebars there. And the whole thing is rotating with some angular velocity. Okay, you guys see that? It's going around. Okay. You're hanging on these handlebars. Now, if you're blindfolded, which way does it feel like you're being thrown? Which way?
To the right.
Does it feel like you're being thrown straight out?
Yeah.
That's what it feels like. That's what centrifugal means. Right? But you only experience that if you're along for the ride on the merry-go-round surface. Right? Here's the weird thing, though. If you are in an inertial frame of reference, like this guy on the grassy knoll over here, he doesn't actually, he wouldn't actually describe any outward acting forces. He would say, no. The fact that you're holding onto those handlebars, that's keeping you in the circular path. There's a force pulling you which way? There's a force pulling you towards what?
Center.
Towards the center of the towards the center. Right? And that force we call not centrifugal, we call that what? Centripetal. Right, there a centripetal force, right? Right. So I'll label it just a force. Right. But yeah, that's you holding onto the handlebars. That the handlebars are holding you into the circle. Right? You guys see that? So this guy along for the ride thinks there's an outward acting force, centrifugal. This guy on the grassy knoll, inertial frame of reference, says, no, it's a centripetal force holding you in. Right? Now, how about this? What if this guy, again, along for the ride on the merry-go-round, lets go of the handlebars? What if he lets go? Uh, which way does he fly off? According to this guy and the inertial frame of reference. Yeah, tangent to his motion. Doesn't he actually fly off this way? So I'll label that V. So he's going to fly off that way. Okay. 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 Now let's switch frame of reference back again. Let's go back to the guy that just let go of the handlebars. Okay. Okay. Does he feel like he's flying straight away from the center?
Yeah.
That's what he thinks. But keep in mind that this whole merry-go-round is rotating with him. So he thinks, oh no, I'm moving straight away from the handlebars, but the handlebars are kind of following along, right? Now that doesn't actually last for a long time though, because at some point the handlebars keep on moving. He just keeps drifting away in a straight line. Okay? But instantaneously, he thinks he's moving straight away. Really smooth and tangent to his path. Yeah. Right. So a little dynamics there. I got Ligma Spencer 67 is back. Anna, Cole, Spencer, Gion. Rotational speed of a space habitat increases the apparent weight of the people inside. Ooh, these guys right here. Spin it faster. Now what? The apparent weight. Yeah, it would also increase. Hey, how about this, guys? What if that image you just saw? What if the cylinder's not spinning at all? What does everybody feel like? They're just floating around, right? Because there's no real gravity. There's no real gravity. They're all just floating around. Give it a little spin, they experience some gravity. It's like a centrifuge, right? The faster it's spinning, the heavier they feel. Heavier a scale would read. Ligma Spencer, 67. Big boy Spencer, Cole, Spencer, Gion. All right, for the win. You guys ready for the win? Who's gonna win Kahoot today? Car. Okay. Car travels in a circle, constant speed. The net force on the car travels in a circle. Yeah, it's always directed towards the center. Because anything that's ever moving on a curved path, there must be some force that acts towards the center. Kind of like I just showed you guys for the merry-go-round, and I labeled it right here. It acts as some centripetal force. Okay. And guys, in the case of a car going around a curve, it could be one of different forces. Guys, what if the road is flat? If the road's flat, it must be what kind of force? Friction. Yeah. And yeah, you would have to have gravity to help that happen too, but it has to be friction. Okay. What if the road is banked? Guys, if the road is banked, could you make the turn even without friction?
Yeah.
You could. It would be what force? Yeah, it'd be the horizontal component of the normal force. Yeah, it sure would be. Okay. How about this? What if you have a tin can on a string and you're rolling it around? What force is actually acting as a centripetal force? The tension in the string. Yeah, tension in the string. How about this? What force is holding all the satellites in orbit around the Earth? Gravitational force. Yeah, and all those forces act towards the center of the circle, don't they? Get that? All right, we're gonna find out who won the Kahoot. With the bronze, Cole. With the silver, Spencer. And the gold, Gion. Yeah, nice job, guys.